with your question. Okay, so first, any additional question on chapter 12 review problems? Okay, for chapter 13.
Doctor,
Yes,
yes, I do have one question.
yes, tell me.
In exercise 5,
Five?
I do believe so. In chapter
Okay,
13.
13 or 12?
13.
13? Okay,
Yeah.
yes. Exercise 5?
Exercise 5.
Yes.
Uh,
Okay,
I I but let me check if exercise 5 or another exercise. Just a minute.
okay. This is 5. This is a problem you are asking about. This one?
بس اتاكد 5 ولا لا بس في واحد من الاكسرسايزز يا 5 يا 6 I do believe. زي
Okay,
فيني عازبك اوكي سوري عم بعذبك يمكن فيني عازبك تلاقي على الفور. I'm
okay.
really
This,
sorry.
yeah, it's fine. Yes, tell me. This is
In
4.
one of the exercises they used the energy conservation method. Uh, but we did not learn the energy conservation
Yes, we will
method.
learn it exactly. We will
Actually,
learn it
okay,
in chapter 14. صح. You can solve the
okay,
problem.
it was
Yes, it's with this one and this one
it,
and
okay
6.
صحيح
In
مظبوط
problem
5
6. Okay.
so
Look, I will do it for you without the conservation of energy using chapter 13. Okay. The idea is the following. You have a skier moving down this system. We have already done something very similar in chapter 13 in class. Okay. But the difference was that in the problem we did in class, they gave us the initial velocity. So you know the initial and final velocity. And for example, they told you, knowing that velocity at b is equal to let's say 9 meters per second, find the normal at b, for example. Okay, here it's more challenging because you don't know what is the velocity at the point of interest. And if you want to get for example, if they ask you to get the normal reaction at c, uh, you know that in this case, why we can think about normal tangential coordinates? Because we said that whenever we know the path of motion equation, so here we have y as a function of x. Okay, so when you know y as a function of x, you can find the radius of curvature rho function of x at any location. And this will give you the advantage of working in un ut, because you say that an at any point, so an can be calculated at any point if I know just x. Okay, because it's equal to the velocity of the at this point square over rho at x. But the challenge also here, if I don't give you the velocity, you should also be able to calculate v as a function of x also. Okay, how to do this? If I tell you, for example, the skier is at x equal minus a, you should be able to calculate the velocity. To do this, we should go back to chapter 12. As you know, chapters are always related to each other. So here we need chapter 13 to apply sum of forces. Sum of n equals man, sum of t equals mat, but also we need the concept of chapter 12 to be able to calculate v at any position x. To do this, let us think together. Okay, you know the initial condition at a, you know the velocity at a. Okay, and you want to get the velocity at any other point. So what you should do here is to determine the acceleration of your skier is affected by what. To understand this, you need to do the free body diagram. So first, let us take any location of the skier. Let's say it's here. So I have, this is ut. and this is UN. And what are the forces acting on my skier? If I want to present forces, so I have two forces, the weight and the normal. So this is the weight, mg. And this is the normal n, okay? First, the acceleration, the velocity is related to acceleration, okay? So if I want to determine v at any position, I need acceleration, which is at, because at is by definition dv by dt. Since at is dv by dt, I need to get information about at, okay? And to get information about at, all I have to do is to project on ut. So I can say, according to my figure, if I do sum of t equals to MAT, okay, I have to project on ut. Let us look at our free body diagram. The normal force is already perpendicular to ut. So we just have the weight, okay? And for the weight, how can I find the angle between the weight and ut? You know that,
Tangent theta equals
exactly, we know
dx.
that ut is doing with the horizontal in angle theta. And we can calculate theta as we have previously seen. Theta is tan minus 1 dy by dx at the point of interest. So we can find the angle theta. Okay? So tan minus 1 of dy by dx. So now, as if we look at our figure, the weight is doing with ut 90, an angle of 90 minus theta. So or we do sine theta or cosine 90 minus theta. So when we project, we just have mg sine theta. Great.
دكتور سؤال.
Now, yes.
يو ان يو ان ويو تي perpendicular مش صح وانه ام جي كمان.
And mg مش perpendicular, no. Normal force is perpendicular to contact. Well, how is your contact line here? It's along the tangent to the path. So if you draw the tangent to the path is along ut. Okay? And since the normal is
اوكي بس
perpendicular.
سؤال.
No.
لا
Yes.
كمل sorry.
So only at point,
انه
only at B اللي هو at the, if you want, at the point where the tangent is horizontal, only at B the normal and the weight will be collinear. But at any other point, you have an angle that
اوكي
is varying between n and the weight.
اوكي وانه يو ان هن بهيدا الكيس هن عزت الاكس او لا.
بلا n و un على نفس axis because the tangent line is along ut and the normal is perpendicular to the contact line اللي هي
بس
tangent.
perpendicular عليهم يعني دائما هن بيكونوا عزت الاكس.
Yes, in this
صح؟
scenario, n is along un always, perpendicular to ut. But in
اوكي
other cases, مثل بالفورمula 1 problem, it's completely different. And you should consider the contact line. When you know where is your contact line, normal is perpendicular to the contact line. هون, the contact line هي tangent to the path. That's why normal is along un. While, for example, بالفورمula 1 problem, ما كانت الكونتاكت لاين هي along the tangent to the path, if you remember.
الان واليو ان.
ساعتها كانت النورمال
يس.
عندها two component, one along UN, one along UB.
اوكي دكتور ثانك يو.
Okay. So here, after you write sum of forces, sum of T equals MAT, M will be simplified. So you get what is AT. AT is G sine theta. Okay. Great. So we're able at least to find a variation of tangential acceleration with position. Now, since we don't have any idea about time, we'll not use AT equal dv by dt. We'll use another differential equation. You know that you can write also AT ds is equal to v dv. So we need to try to think together in a way to relate ds to theta, okay? Because here in this equation, AT is function of theta, and theta is related to position. So we need to get a relation between theta and ds in order to be able to integrate from both sides. So here AT is function of theta, but it should be written as a function, let's say, of s to be able to integrate. So we should do a small geometrical analysis. Okay, let us see what is ds actually. If you take a small displacement ds, ds is along the tangent line. This is ds, it's along ut. And what is theta? Theta is the angle between ut and the horizontal. So this is theta, okay? And the vertical displacement is dy, okay? So this is dy. If I look at my figure, I can relate, okay? I can relate ds and dy. I can say from my figure that ds sine theta is equal to what? ds times sine theta.
To dy.
Exactly. But please pay attention. It's not dy, it's minus dy. Why? It's minus
Then
dy.
opposite direction.
Yes, لأنه according to our selection of y-axis, it's positive up, while s is positive down. So when the s is positive, the sphere is moving downward, dy will be negative. So ds sine theta is minus dy. And now if you replace at by g sine theta, you'll get the following. At is g sine theta times ds equals to v dv. And you can see here that I can replace sine theta ds by what? I can replace this term by minus dy, okay? So I was able to come up with a really very simple relation from a very complex analysis. So my relation is the following: minus g dy equals to v dv. And now if you integrate, can you tell me what do you obtain if you integrate both sides?
بس من وين اجت الماينس جي دي واي؟
Okay. من وين
اوكي.
اجت minus
مش
g?
الحال you replace.
I just replaced. مش نحن قلنا انه according to this triangle ds sine theta is minus dy.
حطيت you put the minus لأنه أخذت البوزيتيف axis مع الموشن لتحت صح؟
مظبوط صح. لانه انا الدي اس هون مع البوزيتيف موشن. So at ds is v dv, okay? بس الواي axis اخدينه upward. So when s will increase, y will decrease. They vary in an opposite way. This is why we should put the negative sign here, minus. And according to the geometry, ds sine theta can be replaced by minus dy. So here now, if you integrate both sides, okay, you will get the following. You will get minus g delta y, because g is constant, is equal to v final square over 2 minus v initial square over 2. Is this familiar for you, Shia? If you study the chapter 14 now, okay? If I multiply by the mass and
Yeah, it's equivalent to u.
this is equivalent to conservation of mechanical energy. Because actually what is happening, guys, if you multiply by m both sides, what is mg delta y minus mg delta y? This is the variation in gravitational potential energy. As you move downward, you gain, you lose gravitational potential energy and you gain kinetic energy, okay? And you know that what is the expression of kinetic energy? It's half mv final square at final state. So if you multiply here by m, you get the final kinetic energy minus the initial kinetic energy equals to what? Equals to the variation in gravitational potential energy. I am losing gravitational potential energy to gain kinetic energy. This is the conservation of mechanical energy. Or also, this is the principle of work and energy. What is the principle of work and energy? Sum of work of all forces. Here, you know, N is doing work in this case, in this problem.
Yes.
The normal. The normal is
No, because it's
perpendicular.
And
no.
yeah.
Okay. The normal is
Yes,
perpendicular
it's
to
equal to
motion.
zero.
It cannot produce any work. So the only force doing work is the weight. And the work of the weight, if you have considered videos of chapter 14, is minus mg delta y. So this represents the work of the weight. Here it's positive as I move downward, and it will be negative when I move up. Okay, so the work of weight is equal to the variation in kinetic energy. So if you start with chapter 12 and 13, you go back to the result of chapter 14, which is or conservation of mechanical energy or principle of work and energy. And here, because the principle of work and energy is much easier, they directly did conservation of mechanical energy. But you are not supposed here to know it, so you can use chapter 12 and 13 as we did. Okay. Any other question on chapter 13 review problems?
Yes, I have a question, Doctor.
Yes.
In this exercise,
Yes, tell me.
can't we just derive the equation of the path?
No, the equation of the path is given. يعني they give you y function of x.
Can't
You
we
mean
just derive it
of
that
time?
way?
What do you mean function of path? Y function of time and x function of time, you mean?
Yes.
Okay. Yes. Look, now once you have
To get V,
now,
we derive with respect to time.
yes, you can derive
Or we derive the equation of the path.
but you should pass by these steps before. And now you got the expression of AT, okay? And you know the expression of AN. If you want to get X function of time and Y function of time, you should now decompose AN, AT into X and Y frame. I will repeat what I mean. Let me, do you see the, let me open a new file to draw it for you. Okay. First, you cannot start from the beginning with AX, AY because you don't have any information. Okay. You start with UNUT. With UNUT, you are able now to get AT. From your analysis, at any point, you can get AT and you can get AN. Okay. Now, if you want to go back to X function of time and Y function of time, okay, you need to decompose A and AT into X and Y. So to do this, you can take a frame here. So you can say, I want to go back to frame X and Y. Okay. I can do it because what is the total acceleration vector? You have that the total acceleration A vector.
Radical AT plus squared plus AN squared.
Yes, or also if you want, it's equal to ATUT. I'm talking as a vector magnitude. Okay.
Okay.
So it's
Plus
AT
N UN.
and UN. And now if you want to decompose into X and Y, you have to project UT UN on IJ. Okay. Yani now you say, what is UT in terms of I and J? All you have to do is to look at the figure. This is UT, okay? And this is theta. Theta is the angle between UT and the horizontal. So if you want to project UT on X and Y, how you can write UT? It has negative I component, negative J component. So it's minus cosine theta I and minus sine theta j.
minus sine theta j.
Yes, exactly. And for an, you can replace to get for un, you need to decompose it also. So this is un. It has a negative x and a positive y component, and the angle here is theta. So when you want to project on x, you do sine. When you want to project on y, you do cosine. So for un, it's minus sine theta I and plus cosine theta j. Okay. And now
Okay,
you
doctor.
sum I components together, j components together. So you end up with axi. At any location, you can find ax and you can find ay. And now you go back to get v function of time. Okay. You use the differential relations. Yani ax equals dvx by dt, ay equals dvy by dt, etc. Okay.
اوكي دكتور، يعني الايكويشن اوف واي اللي اعطونا اياها بالاكسرسايز بس لنطلع
equation
نحن
of
الثيتا
y
صح؟
ما بنستفيد منها to get ax ay
بس نطلع ثيتا.
because it's just y function of x. It's not y function of time. We
اوكي
don't have any information. This is why we didn't use rectangular components. We used normal tangential. But if you have
اوكي
x
دكتور.
function of time or y function of time
ثانك يو.
or any information, for example, of variation with time, you can think about rectangular components. And
اوكي ثانك يو.
welcome. Other question on chapter 13? If you want also, if you found difficulty in any problem, you can repeat it together if you want. Okay. Let me open then chapter 14. Okay, guys, did you have the chance to go over videos of chapter 14?
Yes دكتور، أنا عندي سؤال
Yes, tell me.
exercise 14.9.
Yeah, 14.9. Yes.
آه،
This one?
هيدا problem
Yes.
أخدنا
Yes.
yes
Okay.
تبع plane. أخدنا إنه الديتيوم الريفرنس تبع potential energy أخدناه يا فوق يا على الأرض،
مظبوط.
بس
نعم.
ما كان فينا ناخدها ما كان فينا ناخدها على محل ال initial point تبع البلين، يعني على ال A، لأنه
أكيد you can. Look, the datum selection is free. You can select any datum, and at the end, whatever the location you choose, delta y will not change. يعني YA will change, YB will change, but YB minus YA will remain the same. That's why the selection of the datum will not affect your result at all.
لأنه إذا أخدناها على ال A بتطلع إنه ال initial potential energy
Zero.
بتطلع زيرو.
مظبوط. والفاينل شو طلعت معك؟ Let us do it
ما
together.
بعرف، أنا طلعت معي غلط، بحس إنه
طب let us do it together. Okay?
أوكي.
So if you take the reference at A and you want to get, as you said, V gravitational at A will be 0 because you considered the datum at A. Now at B you are below the datum. And you have a negative gravitational potential. And you should consider what is the distance below the datum. You need to say that VB is minus M times G times this distance d, okay? Now, how to get d? How you can calculate d? D is actually the difference, okay, between this distance. What is this distance here? Look, at the final
And
position, what is your angle? Your angle is 15 degrees.
15.
Yes. So what is the distance here? This distance is 20 meters cosine 15. Okay. 20 cosine 15. You should subtract from this distance. Which one to get d? You should subtract this distance here. And what is this distance? 20 cosine
20 cosine 60.
Okay. So it's exactly the same result, because if you replace, you will get, instead of d, it's minus mg times 20 cosine 15 minus 20 cosine 60, and you will be back to the same result.
أنا طلعت معي غلط لأنه ما عملت minus 20 cosine 60.
Yes, you should do, because you need only the distance from the datum, this one. And you put
Yes.
minus before it because it's below the datum.
Okay, thank you, doctor.
Well, this problem here, for example, will show you how to combine also several chapters. And here you need to apply, you can apply conservation of energy, but also they asked you to determine the maximum tension developed in the cable. So you need force. Whenever you do analysis of forces, you need chapter 13. So you cannot answer the question here before without going back to chapter 13. So you say, I am interested into the maximum tension in the cable. And this tension is along my cable. So it's along UN. Why along UN? Because if I take my problem, what is happening? I have a cord. I have my airplane, okay, and it's swinging. So what are the forces acting on it? I just have the weight, W, okay, and the tension of the cable, T, acting on the airplane. And because this distance is constant, then the path of motion of my airplane is a circular path, okay? So in general, whenever I have circular motion, one of the easiest frames to work with is UNUT frame. So I can now draw on my figure UNUT frame. UT is tangent to the path. UN is along the normal direction. And since I am interested into finding the maximum tension, I need an expression for this tension. And since this tension is along UN, all I have to do is to write sum of n equals MAN equals to mv square. And of course, the velocity is varying with theta, because as I move downward, the velocity will increase, okay? So it is a certain function of theta. So mv square over the radius of the cable, the length of the cable, which is a constant. I have a circular path and the radius is the length of the cable. So it's mv square over L. Now I project my forces. What do I have? I have the tension along UN, so plus T. And I have to project my weight, okay? So according to the figure, if you look at the figure, this is theta. Theta is the angle between the vertical and the cable. So if I look at my figure, theta is here, between the cable and the vertical. So when I project W along UN, I should do the minus W cosine theta. Equals to mv square over L. So now what is T as a function of theta? T as a function of theta is equal to mg cosine theta plus mv square over هلا this problem can be challenging if you want, if one term will increase with theta, one term will decrease with theta. But here it's very clear that as theta will be reduced, what will happen? As you move downward, the projection of the weight will increase, the projection of the weight along UN. So this component mg cosine theta will increase as you move downward. Plus, when you move downward, what is happening from energy conservation view? The gravitational potential energy is transforming into kinetic energy. So as you move downward, V is increasing. That's why you don't need to do any further if you want analysis. Since you need T maximum, T will be max for theta minimum. Because as you move down, mg cosine theta will increase and v square will increase. So T is maximum for theta minimum. So the maximum tension will occur for an angle of 15 degrees. So now to get the value of T, all you have to do is to get what is the velocity when I reach 15 degrees. And to get this velocity, I need to apply or the work and energy principle or the conservation of energy. Okay, so please connect ideas always in your mind. Yes.
In the case of a deceleration,
yes,
then we're gonna have a transformation from the kinetic energy to the gravitational potential energy.
Look, after if you have here you have only acceleration because you only are moving downward and you have an impact after with the ground. And after impact, the analysis is completely different. We'll study it after. But in case you don't have any impact, let's say you have a swinging ball. Okay. First, as you move down, you have an acceleration phase. And the gravitational potential energy is transforming into kinetic energy. Once you reach this position, you start to move up, it will be reversed. And now you will lose kinetic energy and you will gain gravitational potential energy. And if you neglect the friction, you have symmetrical oscillatory behavior. Yani theta maximum from this side is equal to theta maximum from the other side. So I can ask you, for example, what is the maximum value of theta? The maximum value of theta will correspond to a velocity v here equal to 0. So you have complete transformation of kinetic energy into gravitational potential energy.
Okay. وبعد سؤال دكتور مثلا نحن in this chapter first example 14.1.
Yeah. Yes.
هلا نحن كنا عم نجيب يو بي يعني
work of P. Okay.
work تبع بي هلا هلا هي اوريجينلي بس انه عم بسال انا عن الفورمولا هي على طول بي دلتا واي وبعدين نحن عملنا مثل
Okay, no. Look, you have for the weight the formula is minus W delta Y. Okay? For the weight only. Because if you remember in the course material, we derived together, okay, that the expression, so let me put it here. If you take the weight as a force and you consider that y-axis is positive up, the work of the weight is minus W delta Y. Okay, but not for any force because the weight is vertical while P is horizontal here. So you cannot apply P delta Y for the work of P. You need to go back to the concept. What is the concept? I should project the force along motion. The direction of motion is inclined. Okay? And I know that the angle between P and the incline is 30 degrees because these two angles here are equal. Okay, so I should project P along the direction of motion. If you project P along the direction of motion, it is moving in the positive, it's pointing up in the positive direction. So it will do positive work. Okay, so only this component of P, which is P cosine 30, will do a work, while the second component, which is P sine 30 here, will not do any work because it's perpendicular to motion. Okay, so you say since magnitude and angle are constant, no need to integrate. And since P sine 30 is perpendicular to motion, no work. So this is the only component doing work. After you project P along the direction of motion, what is the displacement along this direction? It's 2 meters. So the work is P cosine 30 times delta S, and delta S is equal to 2. For the weight, or you apply the formula directly because it's developed in the course material, minus W delta Y. Or also you can do exactly as you did for P. If you consider the weight, actually the weight is a vertical force. Let me draw it. Okay. I can project it on the direction of motion. It is divided into two components, one perpendicular to motion that will not do any work, and one